Just take a look around you for a second. That screen you're staring at, maybe a book on your shelf, heck, the very room you're in, they all have something in common. And it's something super simple. They're all built on the foundation of a basic four-sided shape, the quadrilateral. So today, we are going to crack the code on these everyday heroes of geometry.
Okay, so what do a smartphone screen, a flying kite, and a plot of land all have in common? I know, it sounds like the beginning of a really bad joke, right? But the answer is actually geometry. They're all quadrilaterals. And trust me, by the time we're done here, you'll have all the tools you need to measure any four-sided shape you can possibly find.
All right, here's the game plan. First, we're going to lay down the basics. What even is a quadrilateral? Then, we'll dive into the family tree of these shapes, from your everyday square to its kind of weird cousins. We'll hit the simple area formulas you probably remember, and then we'll unlock the master keys for measuring any quadrilateral. And to wrap it all up, we'll check out a seriously cool technique used by land surveyors.
Okay, let's get into it. Section 1, four sides, four angles. This is the blueprint for every single four-sided shape. So the name itself, quadrilateral, it's pretty straightforward. It literally means four sides in Latin. Quadri means four, and lattice means side. Simple enough, right? It's just a two-dimensional, closed shape with four sides, four corners, or vertices if you want to be fancy, and four angles. That's the whole deal.
So these are the golden rules, the non-negotiables for any shape to join the quadrilateral club. It's got to have exactly four sides, exactly four vertices, exactly four interior angles, and it's got two diagonals that connect the opposite corners. But there's one more rule, one property that ties them all together. It's kind of like a magic number that's always true no matter what the quadrilateral looks like. And that number is 360 degrees. Yep, every single time. You can stretch it, you can shrink it, you can totally warp it into some weird shape, but the four angles on the inside will always add up to 360 degrees. This is like a fundamental truth of geometry, and it's absolutely key to understanding how all these shapes work.
All right, so we've got the basic DNA down. Now let's meet the family. And this isn't just some random jumble of shapes, it's more like a hierarchy, a real family tree where every member has its own special thing going on.
Yeah, the best way to picture this is like a big extended family. You've got the great-great-grandparent. That's your basic general quadrilateral. And then you have all these descendants that get more and more specialized as they inherit specific traits or have to follow stricter rules, like having parallel sides or all equal angles.
So first up, we've got the parallelogram. This is a quadrilateral with two pairs of parallel opposite sides. And you know what? A perfect example is probably right in front of you. That screen you're watching this on. It's a rectangle, which is actually a special kind of parallelogram.
Now, from the parallelogram, we get even more specialized children, if you will. If you take a parallelogram and you make all four of its sides equal in length, boom, you've got a rhombus. But if instead you take that parallelogram and make all four angles perfect 90-degree right angles, now you've got a rectangle. See, they're both still parallelograms, they just have these extra, more specific rules they follow.
And this brings us to the square, the ultimate specialist. It's like the overachiever of the family. It's got the equal sides of a rhombus and the right angles of a rectangle. That makes it part of both families, and the parallelogram family too. It just checks all the boxes.
Okay, so we know the family, but how do we actually measure the space they take up, their area? Let's start with the easy stuff, the low-hanging fruit, the formulas for the most common, most symmetrical members of the family.
For these really regular shapes, the formulas are just wonderfully simple. A square? Just multiply the side by itself, side squared. A rectangle? You got it, length times breadth. And for any old parallelogram, it's just its base multiplied by its perpendicular height. Nice and easy. Okay, let's try one out. Imagine a parallelogram, and let's say its base is 7 units long. Now to find the area, we need its perpendicular height. That's the straight up and down 90-degree height, not the slanted side length. So let's say that height is 9 units. What do we get? Well, it's just base times height. So 7 times 9, that gives us 63 square units. See? Simple, clean, and it works perfectly for any parallelogram. But what happens when our shape isn't so neat and tidy?
And this is where things get really, really powerful. We're moving beyond the simple stuff now. We're talking about the master keys, the formulas that can unlock the area of any four-sided shape, no matter how weird or irregular it looks.
So here's the big question, right? Because shapes in the real world are messy. A plot of land, a piece of fabric you're cutting, even a shadow on the wall, they're almost never perfect rectangles. So how do we handle the chaos of just a general, irregular quadrilateral? Well, it turns out there are a few absolutely brilliant ways to do it.
The most intuitive way is a classic divide and conquer strategy. You just draw a line from one corner to the opposite corner, a diagonal. And just like that, your complicated quadrilateral becomes two simple triangles. And we know how to find the area of triangles, right? You can use a bunch of methods, like Heron's formula, if you know the side lengths. Then you just add the two areas up. Simple but super effective.
Now, here's a slightly more elegant solution. If you happen to know the lengths of both diagonals and you know the angle where they cross each other, you can use this nifty formula. Area equals 1/2 times the first diagonal times the second diagonal times the sine of the angle between them. Now, don't let sine scare you. It's just a trig function that helps relate angles to side lengths. It's a really powerful little tool for calculating area. Okay, now for the holy grail, the ultimate weapon in our arsenal, Bretschneider's formula. It's named after a 19th century German mathematician, Karl Bretschneider, and this thing is an absolute game changer. It lets you find the area of any quadrilateral, and all you need are the lengths of its four sides and two of the opposite angles. It's the ultimate master key for any four-sided shape you can throw at it.
But what if you don't have angles or the lengths of the diagonals? You know, in the modern world, we often have something even better: coordinates. Surveyors, video game designers, engineers, they use this method every single day. This is the surveyor's secret.
It's called the shoelace formula, and it is pure genius. I'm telling you, all you do is list the x and y coordinates for your four corners in order going around the shape. Then you multiply diagonally down and to the right and add all those up. Next, you do the same thing, but multiplying diagonally up and to the right and add those up. The area? It's just half of the absolute difference between those two big sums. It's kind of like tying your shoelaces, which is where it gets its name, and it works like a charm every time.
So, let's wrap this up. What have we learned? Well, we know now that every four-sided shape is a quadrilateral, and its angles always add up to that magic number, 360 degrees. We've explored the whole family tree, from the basic parallelogram all the way down to the super specialized square. And we've gone from the simple formulas like length times breadth to unlocking the master keys, like Bretschneider's and the shoelace formula, that give us the power to measure literally any four-sided shape we can find.
So you're now equipped with the same tools that mathematicians, engineers, and surveyors use. The world around you is basically a playground of quadrilaterals, from the tiles on your floor to the weird-shaped garden in your backyard. You have the code. So, my question to you is, what are you going to measure first?